So let us continue with our topics in this course. So before we go about formulating the actual mechanics problems, we will get ourselves familiar with a standard notation, and we will also familiarize with the concept of tensors. And we all through the course, as much as possible, we will try to stick to Cartesian. Of course, we will also use polar and cylindrical coordinates, which will be in the later half of the course. In this set of lectures, we will look at what a tensor is, and instead of writing long equations and various number of components of every equation, every vectorial equation, we will try to use the shorthand short form notation, and we will see what we can do with respect to the existing vector calculus that we are familiar with. So let's begin. So this is what we'll do. We'll try to see what is indicial notation. Then we will apply that to vectors and tensors, and then we'll try to do some coordinate transforms. In science, there is no suspense. So tensor is perhaps the only term which is not really familiar to some of you. So let's for now briefly define what a tensor is, and then we will continue with our indicial notations. So what is a tensor? Simplest way of defining a tensor is this. An nth order tensor maps an n-1th order tensor to a first order tensor. Okay. An nth order tensor maps an n-1th order tensor to a first order tensor. Basically, if you are looking at a second order tensor, then it is mapping a first order tensor to another first order tensor. If you are looking at a third order tensor, then it is mapping a second order tensor to a first order tensor. Okay, so that's what we will for now define what a tensor is. Okay, and we will see what all conclusions that we can draw in this lecture. And when it comes to the calculus of this tensors and vectors, we will again revisit this definition. So going by this definition, vector is a first order tensor, scalar is a zeroth order tensor, and what we know as stress and strain are essentially second order tensors, and we also know they are symmetric second order tensors. So we will for now accept this definition of a tensor as an nth order tensor maps an n-1th order tensor to a first order tensor. All right. So with this background, we will proceed. So indicial notation is something which you guys are already familiar with. If you are starting, you have seen this summation on squares of natural integers. So one way you write it is, you write it as sigma p square, where p is varying from 1 to n. And I can replace p with q and then or r, or for that matter, any variable, right? So this is the short form notation. Likewise, in mechanics and to some extent in electromagnetics as well, people use this short form notation, and that short form often comes in the form of indices, because we have vectors. When we write a vector, for example, if you have a vector v, you will write it as vx I hat plus vy j hat plus vz k hat. Why is this called indicial notation? For us as in for engineers, it's usually, all these are v's, just that the components vary. So the index, we typically represent this by an index, vp ep. So we will see that. So essentially, indicial notation revolves around simplifying or representing a long equation in a short form, right? And here I is nothing but square root of -1 in the second expression. Likewise, when you have, how can we represent a vector in short form? It's if A is a vector in the Cartesian reference frame. Okay, all through the definitions, we'll try to stick to Cartesian coordinate system. So if A is a vector, it has the components A1, A2, A3 along X, Y, and Z axis. And the unit vectors along X, Y, and Z axis are indicated by I hat, J hat, and K hat all through this course. All through this course, I hat represents the unit vector along X direction, J hat represents the unit vector along Y direction, and K hat represents the unit vector along Z direction. So we have a vector in Cartesian form, You can write it, you know already, you can write this is one way of representing and this is the second way of representing it. You can write the same vector in matrix form as a column matrix with the components listed. And in the indicial form, this is how you write it. Okay, I've sort of written in a shorthand form. So a vector in indicial form is written in this style. As you can see, P can be replaced with any other arbitrary variable. And that is why this index P is called as a dummy index. Okay, or also called as a repeating variable. Okay, that's the first rule. So whatever is repeating is the repeated index, or also called as dummy variable. Okay, so now you know two other forms of representing a vector. This is the third form, this is the fourth form. One is indicial, one is matrix form, one is component form, and one is in the direct vector vector symbolic notation. So there are about 4 ways now you know about representing a vector. Right, so let's continue on this. So as I said, we will use indicial notation to represent vector sentences because that's what we encounter in our course and broadly in mechanics as well. Right. So, and what is the need apart from writing it in shorthand notation? The indicial notation also helps us simplifying other expressions. For example, if you have to multiply the 6 components of stress with the 6 components of strain in order to determine the internal energy density, this you can do it in maybe in 4 variables rather than writing 12 expressions involving 24 terms. Right. So it helps us to do our mathematical operations. And primarily in indices, there are two kinds of indices. One is the free index and other is the repeated index. Just like in the previous slide, when we have written A, vector A is AP, EP, right? P is the repeating entity, right? So this is the repeating index. Okay, this signifies summation. There is no need for us to specially write it as sigma AP, EP hat. There is no need for us to write this as and P running from 1 to 3. All right. So there is no need for, if there is a repeating index, it implies summation. A repeating index implies summation. You don't have to write this. In fact, it is better that you avoid writing this sigma notation. Repeating index implies there is a summation. Whether you want to do it in 2 dimensions or 3 dimensions is dependent on your problem at hand. But repeated index implies summation. So this automatically implies A1 even hat plus A2 E2 hat plus A3 E3 hat. Okay. So, and we will see what a free index is in a minute. But since we have already defined a vector in indicial form, you might as well learn that this is a repeated index. Right. So I have this expression Pi is Qij Rj. So I will expand it in 3-dimensional Cartesian notation. I can as well write it in the old style as repeating over J. But from looking at this expression itself, you can see that J is repeating. So J is the repeating index or the dummy variable. And I is not repeating. If I look at this expression on the right hand side, it is only J that it is repeating and I is not repeating. So I is the free index and J is the repeated index. And since it is J is a repeated index, it implies summation over J. So in other words, if I expand it, this is what you get. You change the value of I on one on the left hand side. Likewise, on the right hand side, you will end up changing the values of I. So in here, if I look at the first expression, I is 1 and J varies from 1 to 3. The second expression, J is 2, I is 2, whereas J varies from 1, 2, and 3. Likewise, in the last one, I is equals to 3 and J varies from 1, 2, 3. All right. So that's all there is to it. Popularly, this notation is also called as, is also referred to as Einstein notation or summation notation. We will stick to one term, which is indicial notation. All right. And you also know, you can also, now that you know a vector, we can write a vector in its indicial form and simply add it. Or now you also know that you know how to write it in component form, sorry, in a matrix form. You might as well add the corresponding components in a column matrix. All right. So we will see what happens to a vector when it is when the coordinate system is rotated. So I hat, j hat, k hat are representing the unit vectors along the original coordinate system, and p is a point with coordinates x, y, z, and the corresponding vector from the origin to the point p is the position vector r. And what has been done here is the original coordinate system has been rotated by a particular angles with respect to x, y, and z. It doesn't matter which order you rotate, it has been rotated in a random fashion, keeping the origin at the same place. That is the key. If you have moved the origin, then you might as well account for that as well. But for now, let us start with the rotation aspect. So x, y, z represents the original coordinate system, and x prime, y prime, z prime, or the corresponding unit vectors are I hat prime, j hat prime, and k hat prime. These are the new coordinates. These are the new unit vectors in the rotated coordinate system. Our objective is to identify, using indicial notation, to identify the coordinates of the same position vector. The position vector remains the same. Okay, you can call this as position vector, electric field, or any other vector in general. R I have used, this is the position vector is something which we'll encounter often. So I've used R, but it appeals to any vector. You have a vector in a particular coordinate system, and you are rotating the coordinate system, keeping the origin as the same, and we wish to identify the corresponding components of the same vector in the new or the rotated coordinate system. So the position vector R is this, and in the new coordinate system, it is x prime, y prime, and z prime are the corresponding components. And as I just said, our objective is to identify x prime, y prime, and z prime in terms of x, y, and z, provided we know what are the corresponding angles between the new axis and the old coordinate axis. Right? We know R, which means we know x, y, and z. R is same as r prime because it is representing the same vector, just that we are trying to view them in different coordinate systems. We have used the notation prime for R as well. Our objective is to identify the components of the same vector in the new coordinate system. All right. So the knowns are x, y, z, and the rotation angles of each of the axes. Right. And the unknowns are x prime, y prime, and z prime. I hat prime, j hat prime, and k hat prime still remain mutually perpendicular. We are not altering or compressing the coordinate system or skewing the coordinate system. The original coordinate system has been rotated with about the origin in about the various original axes, keeping the origin as the same. So we need to identify the new components. So what do we do? Since they are all mutually perpendicular, let's take the dot product. So I'm taking the dot product of the original position vector. R is xi hat, y plus yj hat plus zk hat. I'm dotting it with the new unit vector along x-axis. So I'm dotting with I hat dot, I hat dash dot, and then this is what we get. R dot I prime is nothing but x prime. So x prime is x times I dotted with I prime, y times j dotted with I prime, and so on for the z component as well. Likewise, we can end up, now that we written what x prime is in terms of x, y, z, and the unit vectors of the old and new axis, new coordinate systems. Likewise, one can identify y prime and z prime in terms of x, y, z, I, j, k, and I prime, j prime, and k prime. So now that we have defined, now that we have these terms I dot I prime, j dot I prime, k dot I prime, I'm going to call them as qxx, qxy, and qxz. So you realize you can get similar components when you take when you identify y prime and when you identify z prime in terms of x, y, z, I hat, j hat, k hat, and I prime, k prime, and j prime. So essentially, this is what you have. X prime, y prime, and z prime in terms of these new definitions. See, we know I, let's start the stylus, I, j, k are all unit vectors. So their magnitude is anyway known. Likewise, I prime, j prime, k prime are also unit vectors. So their magnitude is also known. What is not known is if this was the original coordinate system, x, y, now we have a new coordinate system, x prime, y prime. This is the diagram which you guys are familiar with in the standard mathematical coordinate geometry class. Now we are doing the same rotation in 3 dimensions. Right now we are rotating it about the z axis. Whatever is shown in this box, the axis is rotated with respect to z axis. Now we are rotating it in 3 dimensions. So effectively, you can write, since you know how much you have rotated, which means you know the angles between all these 3 new coordinates, new axes. So since we are rotating, so we know the angles, which means the corresponding dot products can be evaluated. The angle between I and I prime is known. The angle between I prime and j is known. Likewise, the angle between any 2 unit vectors, whether they are in the original coordinate system or across the coordinate systems, all of them are known because we are rotating the coordinate system, which means the new coordinates can be written in terms of the old coordinates using the cosine matrix. This matrix is also called as transformation matrix. So I've switched now from indicial to matrix to back to vector notation. So this is indicial here, right? This is indicial, and we are from matrix notation. We are writing it as a in vector notation. So this was the original position vector. We know it remains the same, just that the components vary. So R is same as R prime, just that they are in different notations. The best way, the more correct way of writing this is R prime is Q, which is a matrix. It's not a tensor. We have to be careful there. Although I've used this, let us not use this particular symbol. Please use a matrix kind of symbol. So Q is called as a transformation matrix, right? So you know the rotations, you know the angle between the old coordinate axis and the new coordinate axis, and hence you can identify this transformation matrix. Since you know R, you can identify R, which means if you know your original coordinates, you can identify the new coordinates of any vector. And if you do some simple mathematics, you should be in a position to prove Q transposes identity is equals to identity matrix, which is 3 by 3. 3 by 3 identity matrix. But you can as well write this in indicial notation. Okay, what is this? This is not different from anything that we have seen in the previous slide. This is what we have seen in the previous slide, and that's what I am writing again. All right. So this is how coordinates are rotated. When a coordinate system is rotated, this is how you identify the coordinates of the particular vector. A similar thing can also be extended for tensors. So when we deal with tensors, we will revisit this concept once again. All right, so let us sort of give a quick recap. Previously we used R, so now I'm using a different notation. I have a vector A whose components are AX, AY, and AZ in the original coordinate system. And the primed coordinates, primed components are the components in the rotated coordinate system. And if you know the coordinates in one coordinate system, one can identify the coordinates in the other coordinate system. And you can do this in matrix form, as well as you can do it component wise. I've just tried to do what we have been, what we started this lecture with, trying to write it in indicial notation. So A prime, you can write it this way. There's a slight skip that has been made here. Often when you're using indicial notations, instead of operating with X, Y, and Z, one operates with X is represented with 1, Y is represented with 2, and Z is represented with 3. So effectively, QXX it becomes Q11, QXY becomes Q12, QXZ becomes Q13, and so on. All right, and AX, so A is now equal to A1 I hat plus A2 J hat plus A3 K hat. All right, so in component form, I'm just rewriting the same first term, and likewise you can have the second term and the third term. Now you don't have to really, this implies a summation. So I've written it for our convenience sake, but we don't have to use this summation. So if we just write this, since there is a repeated index, J is a repeating index, which means the summation is over J. There's a slight typo which I have made here. So this will be Q11 A1, Q12 A2, Q13 A3. Right? So that typo, please do take care of it. So Q11 A1, Q12 A2, Q13 A3. All right. So likewise, so this is something which we have already discussed. Like since J is the repeating index, J is the one which is repeating, J is called as dummy index, and you can always replace a dummy index with another index. It does not matter what is the name that is being used for the dummy index. Why are we calling it dummy? Because that is the one which is repeating, and it does not matter what that dummy entity is represented with. So J can be replaced with K, can be replaced with L, or for that matter, any symbol. All right. So your AI prime is QI P AP. Okay. Here I've written in J and K, and here I'm writing it the same in another dummy index P. So there are certain rules for this indicial notation, which are the following. First is dummy variable. If something is written twice, which means you need to sum over it. So A11 is A11 plus A22 plus A33. And if you are only dealing with 2 dimensions, it means A11 plus A22. Likewise, since it is a dummy variable, I can replace I with any other variable. Okay, so repeated index is what is referred to as a dummy variable. If there are more than one dummy variable or a repeated index, then the summation occurs over all of these. What does this mean? It is something which we have seen. It is an extension to what we have seen. If we see this expression, see our previous expression, we go back to the previous slide. Yeah, this one. Say, let me erase this. Right. So if I consider this expression, there is only on the right hand side, there is only one variable which is repeating, which is J. I is not repeating. So I is a free index and J is a repeating index. So there is only one variable on the right side, which is dummy, which is J. However, if we look at this particular expression, Cij, Ai, Bj, both I and J are independent of each other. That's one. And second, both of them are dummy indices, just that they are not identical. All right. So first I can I will just do the summation over I. So I'm expanding wherever there is I. I'm just summing it as, I'm replacing I with 1, 2, and 3 and adding those terms. And then I'm summing it over J. So this is the first term and this is the further terms. All right. So summation occurs over both the variables. I and J vary between 1, 2, and 3. And hence you get a total of 9 terms. So this is the second rule that we should know, that if there are more than one dummy variable or dummy index, then the summation occurs over all of them. If you want only partial, then you please be specific. This alone represents 3 terms. This alone represents 3 more terms. This alone represents 3 more terms. Right? And repeated index is not repeated twice. A bit of a paradoxical statement, Let's see what it is. So you cannot write this form. For example, sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square. You cannot write going by the rules of repeated index as this type. Why? Because it gets confusing once you get to the notation of principal stresses. Okay, so you don't repeat it this way. Okay, so this is a rule just to avoid confusion. Okay, you can do these kinds of things, Cij, Ai, Bj and all, or you can even have Aii, that is all fine. But you cannot repeat the repeated index in a particular way as in the way shown here. Right, it's kind of a rule to avoid, which is a rule which is used to avoid confusion. Number of free indices must be the same on both sides of the equation. So here in this expression on the right hand side, by now you might have got the concept. P is the repeated index or the dummy index, and K is the free index. Okay, so it has to be K on either side. Okay, so now notation of free indices must be the same on both sides. This statement actually does not hold true. So this is actually not for here. So if it is K here, it has to be K here. You cannot have something different like the way it is written here. All right. So the notation must be the same. And the number of free indices on either side should also be the same. We have shown with respect to one variable K in this particular equation, but you can as well expand this into multiple indices, which we will see maybe in 2 weeks time. Likewise, the second one in the notation of the free indices also must be the same. For example, on the left hand side of this last equation or inequation, on the left hand side you have I component, whereas on the right hand side there is no I component, which basically is not really tallying up. A free index must tally on either side. The last one is when you are using just 2 dimensions, people tend to use alpha and beta notation instead of I and j or any other particular form of variable. So if there are 2 indices, if the problem is of 2 dimension, you are dealing with only planar geometries, you might as well stick to the alpha beta notation. Now let us look at some elementary vector operations, which we all of us are familiar with since 11th standard. I'm trying to recast what we know into what we just learned, which is the indicial notation. So if A is a matrix, then the corresponding components are A, I, J, right? And I can write any matrix as a combination of symmetric matrix and anti-symmetric matrix. All of us know symmetric matrix is that matrix where the transpose of it equals the original matrix, and anti-symmetric matrix is the transpose equals the negative of the original matrix. So you take any matrix, you can add them and you can split them into symmetric and anti-symmetric parts, and this is how you do it. You take its transpose and you subtract it. So you're going to add its transpose and also subtract it. The first one is the symmetric matrix. If you can realize, if you can see, this is the simple bracket, and the second one is the anti-symmetric matrix is represented by a square subscript. This is the anti-symmetric matrix and this is the symmetric matrix. You replace I with J in the first one and J with I, you would end up with the same matrix. Whereas if you replace in the second parenthesis I with J and J with I, you would get the opposite of it. You would get the negative of it. So that's why it is anti-symmetric matrix. With respect to matrix, again, we will revisit this when we start looking tensors more formally. But since you are familiar with matrix notation, I thought you might as well revisit this. Kronecker delta. We all know what Kronecker delta is, which is delta ij is 1 if I and j are the same, and it is 0 if I not equals to j. So E for us we have been using E to represent a unit vector, right? We've been using E cap to represent a unit vector. So EI and EJ are two unit vectors in a particular coordinate system, in a particular Cartesian coordinate system. And if you multiply those two unit vectors, depending upon whether they are, when I mean multiply, as you can see, it is dot product that I'm referring to. So the dot product of two unit vectors is either 1 or 0, or you can as well represent it in terms of a matrix notation. Because all we know is I, J, and K can vary between 1, 2, and 3. Right? So that is how this Kronecker delta delta Ij is represented. This is its definition. And it's the same definition in matrix form. This is in component form. This is in matrix form. Alternating or permutation symbol, also called as Levi-Civita tensor. I've deliberately tried to avoid the tensor term. So I've said alternating or permutation symbol. This is its definition. There is not much to debate. This does show up when we are when we have to represent the cross product. So if you have two vectors A and B, we will try to now rewind what we know in vectors using the indicial notation. So addition is something which we have seen already. Two vectors A, this is the vector notation, indicial notation, matrix notation. Matrix representation of a vector is just a column vector which is n rows comma 1, depending upon what is the number of independent components of your coordinate system. Right. So we'll start with vectors, simple addition, and scalar multiplication. It remains the same. So the scalar just multiplies to the original amplitudes or original components. The dot product, A dot B, I can write A as AI, EI, B as B suffix J, and E, J. Right? AI and Bj are scalars. Right? Those are scalar components of a vector. So I can as well simply multiply them, AI, Bj. Then I have two unit vectors, EI hat and EJ hat. EI dot EJ, as we have seen in the previous slide, EI, rather in the one before to that, EI dot EJ is nothing but delta Ij. And delta Ij survives or has a value only when I equals J. EI dot EJ is nothing but delta Ij. So I'm going to use that concept here. So yeah, this is what we have. EI dot EJ is nothing but delta Ij. So we have AI, Bj, delta Ij. And we know delta Ij as a non-zero value only when I is equals to 1. So when I equals to J equals to 1, so that's when we get the first term. And then it survives when I is equals to J is equals to 2. That's when you get the second term. And when I is equals to J is equals to 3, we get the third term. All right. So hence a dot product simplifies this. Norm. Norm is nothing but the magnitude. So let me erase this region. Right. I'm using the same notation. I'm just replacing vector B with vector A and taking a square root. Right. Same EI dot EJ is delta IJ, and this will survive only when I equals J, and hence you get the norm as this. Right. Cross product, you again use the alternating symbol, alternating or permutation symbol to represent it in one shot. Right. You can as well write cross product in terms of matrix notation as well. Please do that. Then scalar triple product, you're taking this and dotting with one more symbol, one more thing. So we will correct this particular expression as we go towards next lecture. Okay, so that is it with respect to this particular lecture. All right, so in the next class we will start with formally defining what a tensor is, and we will try to see what are the tensorial properties and why we should learn them. So the last part in the next lecture, we will try to revisit this part as to how does one come from here to here. That does involve one more line of dot product, which is what we will try to do. All right. So I will see you guys in the next class.